Mr. Belden. This is part 2 of chapter 1, section 3. So what you'll notice here is now we're going to do other roots other than square root. We'll do some square roots too, but that was in the prior section. And you notice this looks very much the same as the rules for square roots, right? Now we're just calling them nth roots, and it's the same product and quotient rule. The only thing now we're specifying is we're just making a distinction between odds and evens because you can have an odd number of negatives and get a negative outcome. If you have an even number of negatives, that is not negative, right? So when they cancel each other, a radical and a root, they become positive like they did last time with a square root. Same thing as fourth and sixth root this time. So you have to be careful of odds and evens when doing these ones. Other than that, the rules and the processes are the same. Okay, so let's do some examples, both numerically and algebraically. So if I want to do the third root of 64, the index number is now 3. So I don't want pairs of things. I want groups of 3. So 64, if I break that down, is 8 times 8, right? Which in fact is 2, 2, 2, and 2, 2, 2, right? Let me rearrange that 2 there to shift it over a little bit. So I have 6, 2. So if I rethink what that really means, okay, that is the third root of 2 to the third and 2 to the third, okay? Because I have two groups. So what I'm really looking for is groups of 3 this time because the index is 3. So that really gives me an answer of 2 times 2 for an answer of 4. Okay, so if you think about it, what is 4 to the third power? All right, well, let's do that out. All right, calculator. 4 to the third power is 64, right? Because it's the inverse operation, right? Because if I do the third root of 64, right, I get 4, right? Or the third root of 4 to the third cancel each other, gives you 4, right? So you're kind of getting the idea here. Okay, so let's try the 32. So if I do 32, I'm going to ignore the negative for a minute and do, so 32 is 4 times 8, which in fact is 2, 2, 2, 2, 2. Okay, here's the thing though. It's not positive, it's negative. So all of these are negative, correct? Okay, so what I really have here is the fifth root of negative 2 to the fifth, which cancels and leaves you with a negative 2 answer. Okay, so we do negative 2 to the fifth power, you will get negative 32. Okay, so understanding the odds versus evens and negatives, now we can conclude that this answer is negative 2 because a third root cancels a third exponent, right? Because an odd number of negatives is negative. However, the next question looks very similar, but the answer is positive 2. Okay, because yes, they cancel each other, the operations, but the exponent had to have happened first, which would have given you a positive interior because you went to the fourth exponent. Okay, so keep in mind odds versus evens. All right, next one, uh, 24. So this is the third root. So 24 is 4 times 6. And so that is 2, 2, 2, and 3, right? So there's only one group of twos, right? So that gives me the 2 third roots of 3, right? Because 2 to the third power is the only thing that can come out in the group. So that is a non-perfect radical. All of the prior answers were perfect ones because everything came out and there was nothing left inside. Okay, so the next one, if I do this, it is 8, which is 2, 2, 2, and 4 is 2 and 2. So neither one of those have a group of 4 of anything because it's fourth root. But I can use the product rule to combine them. 2, 2, 2, 2, 2. And now I do have a group of 4. That's 2 to the fourth power, correct? So I have 2 fourth roots of 2. So that's another non-perfect radical, right? You can rewrite that one more step if you need to, because that is the fourth root of 2 to the fourth times 2, right? Again, you don't need to do as much detail as I do. I'm doing it extensive detail because it's a lesson. Okay, 81 divided by 16, I don't know about that. That's not going to work out all that well, right? But I can do the fourth root of 81 over the fourth root of 16, right? using the quotient rule of radicals. Because again, the quotient rule and the product rule of radicals applies to square roots and any other root too. The trick is they have to be the same root. They both have to be fourth, or both fifth, or both third. They have to be the same radical to actually work. So this is the fourth root of 3, 3, 3, 3, because 9 times 9 is 3 and 3, which is 81. And 16 is 4 times 4, which is 2, 2, 2, 2. So what's important here is I have 4 2's and 4 3's, which gives me an answer of 3 over 2. So that is a perfect radical. Everything came out. Okay, so we used product rule, we used quotient rule, we did the simplification using primes. So the last thing is adding and subtracting, which we know from kindergarten to college. You can only add or subtract like terms. Okay, so 16 and 2 are not like radicals, but we can break this down into the third root of 2, 2, 2, 2 minus the third root of 2. So I do have a group of 3 here, right? So this is 5 times 2, third roots of 2, minus 11, third roots of 2. So what I really have here is 10 third roots of 2 minus 11 third roots of 2. So 10 minus 11 is negative 1 third roots of 2. That's not a very good negative 1. Let's change that. Okay, that's good. All right, pause the video. Try the student problems for yourself. Okay, so 81 is 9 times 9, which is 3, 3, 3, 3. So there's 4 of those in there because this is really fourth root of 3 to the fourth. So I get an answer of 3. So that is a perfect radical. All right, so 243, and look at the big numbers. Remember, look, is it divisible by, 10 or 5 or 2? No, it's not. But if you add up the numbers, 2 plus 4 is 6, plus 3 more is 9, right? That means it's divisible by 9 and 3, isn't it? So either one is sufficient, correct? So I'm going to break this down. I'm going to ignore the negatives. So that's what, 9 times 27, correct? So again, 2 plus 4 plus 3 is 9. So that means it's divisible by 9 or 3, because 9 is also divisible by 3, right? Okay, so that is the fifth root of 3, 3, and then 27 is 3, 3, and 3, right? But again, this is negative, so these are all negative. And there's 5 of them, so this answer is in fact negative 3, right? So negative 3 to the fifth power is 243. Okay, knowing that same premise, this must be negative 129 because the operations cancel, right? But this answer over here is positive 251 because it's even and the exponent would have happened first, which would have made it positive. Okay, so everything so far is perfect. This next one is the third root of 40, which is 2 times 2 times 2 times 5, right? 4 times 10 is 40. So there is a group of 3 2's. So this is 2 third roots of 5. So that is a non-perfect radical. Okay, next one is the fifth root of 2, 2, 2 twice. Neither one of them have enough 2's, but I can use the product rule to combine them since they're the same radical of fifth root. Let me fix that up a little bit here. And I can get the fifth root of 6 of these. 1, 2, 3, 4, 5, 6 of them. I can take 5 of them in a group, and I can get 2 fifth roots of 2. Okay. All right. Last two. 125 divided by 27 does not work out nicely, but I can use the quotient rule since they're both the same radical. So this is the third root of 5 times 5 times 5, because 25 times 5 is 125, and 27 is 3 times 9, which is 3, 3, and 3. So that guy, in fact, gives me 5 thirds, because it's both groups of 3 for a third root, so that is a perfect radical. And the last one here, 81 and 3 are not like terms. However, 81 is 9 times 9, which is 3, 3, 3, 3, correct? 9 times 9 is 81. Okay, so I have a group of 3 here. So 3 times 3 third roots of 3, there's a lot of 3's in this problem, minus 4 third roots of 3 really means 9 third roots of 3 minus 4 third roots of 3. So these are like terms now. 9 minus 4 is 5 third roots of 3. Okay, and now that is the end of part 2.